All right. Well, welcome everyone. We're very happy to have Jozef Skokan from London School of Economics, who's going to tell us about clique factors in randomly perturbed graphs. Take it away.
All right. Thank you very much, Deepak. And well, thank you, Sandra, for inviting me. As I said before, it would have been much nicer to be together in New York with you, but at least we can talk. And well, I can tell you a little bit about a work, which is a joint work with Julia BoԻďttcher, Olaf, Parczyk, and Amedeo Sgueglia. Surprisingly, for once in my life, I have a talk where all authors are from the same university. So that doesn't happen that often, but it happened this time. So what is this all about? Well, this talk is about marrying some deterministic problem with some probabilistic problem. So what I will do, I will start to introduce the questions maybe from deterministic point of view, then from probabilistic point of view, and then show you how to marry these two together. And as a matter of fact, a person who is responsible for this matchmaking is actually Ryan, sitting in the audience. Like that. So let's start. Okay. So the first thing I would like to talk about some problems which are very natural in extremal graph theory. And the title is self-describing, minimum degree threshold in graphs. So a typical question is, what's the minimum degree threshold that makes sure that a graph G contains a given spanning subgraph H? Okay, so you choose H and you try to see when your graph G contains this subgraph H. So natural example over here is, of course, Hamiltonicity. So Dirac in 1952 shows that n/2 is the threshold for appearance of the Hamilton cycle in a given graph with at least 3 vertices. And of course, this condition is optimal and cannot be decreased to anything anything smaller. Now, another example is Heinal and Semeradi theorem from 1970, which determines the minimum degree threshold for perfect KR factor, right? So perfect KR factor is the collection of KRs, let's say triangles, that spans our graph on n vertices, okay? And this min degree is 1 minus 1 over r times n. And then after some effort, this was generalized to arbitrary graph H. So if you want to find a perfect H factor or tiling of the graph G, then the minimum degree condition is given by this strange looking formula. So it's 1 minus 1 over chi star of H times n plus constant depending on H only. And this chi star is a parameter which relates to chromatic number of vertices of H, and parameter of sigma H. Some of you might have seen this sigma H. So this is the minimum size of the smallest color class in coloring of H with chromatic number of H colors. And this number can be anywhere between 1 and half of the vertices of the graph. All right, so this is a crash course to the minimum degree threshold in graphs. So now let's look at the random version of these things. So first of all, what's the random graph GNP? Well, this is a model over a vertex set of integers where vertices are integers 1 through n. And for every pair of vertices, we pick an edge with probability p independently for every pair. Okay. And now in this model, a function Tn will be called a threshold for some property alpha. So let's think about all graphs which contain a triangle. And so for this property, Tn is a threshold if the following is true. We look at the probability that GNP has this property A. And when we take limit as n goes to infinity, then this will be either 0 or 1. It will be 0 if the probability that we choose is much smaller than the threshold. And it will be 1 if this probability P grows much faster than Tn. Okay, so it's little o and omega. And I hope I don't have to define what this means exactly. Does this make sense for everybody? Or am I losing somebody already on slide number? Well, I hope not. All right, so it's not clear that such a threshold should exist. And actually, Bolobar and Thomason proved in 1987 that if you take any non-trivial monotone property, then such a threshold exists. Here, monotone means that the property is closed under addition of edges. So if you take the property that your graph G contains H as a subgraph, then this is a monotone property, right? Because if graph contains H, then every supergraph contains H as well. On the other hand, if you look at the property of containing H as induced subgraph, then of course by adding edges you can destroy this property quite easily, right? All right, so now we know what's the threshold. So what are the typical questions in this area? Well, for given spanning subgraph H, we would like to determine that the threshold for G and P to contain H as a spanning subgraph, well, is something, right? And the first question asked and resolved was about the Hamiltonicity, where Porsche in 1976 proved that the threshold for this property is log n over n. Okay, then going back to our earlier example, when we look at the Heinal-Samaredis theorem and the minimum degree threshold, so this was proved in 70s. It took much longer to find a threshold for G and P to contain a perfect KR factor. So actually it was Johansson, Kahn, and Wu in 2008 who proved that this threshold is given by this formula. Okay, so in this paper, they conjectured the threshold for this perfect H factor for every H. They resolved the case.
Can you remind me what a H factor is?
As before, H factor means that you take the copy of your graph H and you try to find copies of H which do not overlap in vertices and cover all vertices of your graph. So that's a factor, right? So triangle factor is a collection of vertex disjoint triangles that span all the vertices of your graph. Make sense?
You don't need to hit all the edges.
No. It's about covering vertices, not the edges.
All right. Thank you.
All right. So they resolve the question when H is a strictly balanced graph. What it means is that it's for graph who have a density largest from all of the subgraph of H. And then later, Gerke and McDowell gave proof for different class of H's. They are called non-vertex bound graphs. I will spare you definition. It's really not important for this talk. But the problem is still open for some graphs H. And maybe you would be curious to know that maybe the simplest examples of the graph for which this is not resolved is if you take the square and you give it a hat. Okay, so if you want to find the threshold for random graphs to have a factor with copies of this house, then that's still some log factors of the conjectured answer. All right, so we know we have now a nice question for the random graphs. So we try to see when the spanning subgraph containing, which is a factor of a given copy of H, appears. Okay, or we are looking for a threshold where the graph of large min degree contains such a factor. So how do we marry these two things together? Okay, and the answer is that we will look at the randomly perturbed graphs. And so here the question is that we don't start from empty graph, right, with n vertices at which we throw some random edges, but we start from some arbitrary graph, usually dense, and we would like to know how many random edges we should throw in to this graph such that the resulting graph almost surely contains a given spanning subgraph H. Okay, so in other words, you take your favorite graph G, which is not Hamiltonian, and you would like to know how many random edges you need to throw in to guarantee that suddenly your spanning subgraph H, so your Hamiltonian cycle will appear. Okay, and so this was formally defined in a paper by Bowman, Fries, and Martin in 2003. So the So the model will depend on two parameters, alpha and p. So for this alpha and p, you take a G alpha, which is a graph on n vertices with minimum degree at least alpha n. And then what you do is you take a G alpha and you take a random graph G and P on the same vertex set, and you take their union and you call this randomly perturbed graph. Okay. And now our question is revised into the following form. Given alpha, determine the threshold at which this graph G alpha union G and P contain almost surely a given spanning subgraph H. And you would hope that the fact that you start from some dense graph instead of empty graph will help this random graph to get the spanning structure faster. So you would expect that this threshold for this density, for this probability P will kind of go a little bit down. Okay, and usually this changes by some logarithmic factor. All right, so let's look at this question for the Hamiltonicity. So we would like to determine the threshold Tn at which this perturbed graph G alpha union G and P contains asymptotically almost surely a given spanning subgraph H, and think about a Hamilton cycle. Right? So what does it mean? So there are two parts to this story. So one needs to show that if your P is little of this threshold function Tn, then for every n, you must be able to find one example of n vertex G alpha, such that if you take the union of G alpha with G and P, then asymptotically almost surely, it doesn't have a perfect H factor, okay? So on one end, you will have to find a construction of this G alpha, such that if you throw at it random edges with that given density P, you will not be able to find a perfect H factor. Okay.
One question.
Yes.
So here, are you saying H is a spanning sub?
Obviously, I wanted to talk about Hamiltonicity, and copy paste gave me their H factor instead of Hamilton cycle.
Right. Yeah. Okay. Just making sure.
But also it helps to explain how this question from earlier was rephrased. Okay. And then if you want to, and the second part to the story is that if you are above the threshold, so if your probability P grows faster than the threshold, then regardless how you choose your starting graph G alpha, if you take a union of G alpha with G and P, then you have to find either your perfect H factor, or if we talk about the Hamiltonicity, we need to find a Hamilton cycle. Okay. So the theorem that Bowman, Fries, and Martin proved in 2003 is that for every alpha, you find a constant C that depends only on alpha, such that if the probability is at least C over n, then asymptotically almost surely, this perturbed graph is Hamiltonian. Okay. So how does this result come together with everything that we know? Okay. So if your alpha is equal to 0, okay, then your minimum degree is at least 0. So that means you have to take into account that you start from the empty graph, right? So you are in the case of G and P, and in G and P, you need log n over n for appearance of Hamilton cycle by the result of Poisson. Okay. For alpha, at least 1/2 over here. And if you have a graph with minimum degree n over 2, then you have a Hamilton cycle and you don't need any random edges, right? So the threshold is actually 0, right? And if you are between 0 and 1/2, okay, then this result by Ryan and his co-authors tells you that the threshold is, well, 1 over n, right? So if you have at least probability C over n, then you will find your Hamilton cycle, okay? And so that would show you actually that the threshold is upper bounded by this constant over n, but constant is irrelevant for this notation as we introduce it over here. And if you want to show equality, you have to show this statement. And how do you show it? Well, if you take the suitable, unbalanced, complete bipartite graph, right? Then if you look at this a little bit more, then actually it will show you that what we have over here is actually the right threshold. So if you take this unbalanced, complete bipartite graph, then regardless, if you don't throw enough edges into it, you can show that actually you need to put there linearly many edges, and so that tells you that this is the right threshold in this particular setup. Okay, and so important thing is to really see that we have a decrease of probability threshold by a log factor, right? So from random case where the threshold was log n over n, we came to the threshold constant over n, or 1 over n, and so that means we save this log factor by considering starting point to be a graph with positive or with linear minimum degree. Okay, so this is the setup. Yes.
So here in the definition, I see for a given alpha, you get to choose the G alpha with that lower bound on a degree. Is there any interesting thing in taking all? Is it possible to get a theorem where you allow any G alpha, or you have to say particular G alpha in the theorem?
Oh, that would mess it up, because there will be graph for which, I mean, what would you gain out of it? Oh, yes, so it will really mess it up, right? Because you can show that for some graph with such a min degree, okay, you don't need any random edges, right?
Okay, right, thank you.
Anything else before we move on? I like questions, right? It makes it more interesting. All right. So okay, I will forget now about Hamiltonicity for a little bit. So we will talk about the factors, and especially we will talk about the factors where we try to cover everything by the copies of the complete graph on our vertices. Okay, so again, if I have alpha is equal to 0 and I'm in the random graph, then I know that the threshold is given by this Johansson-Kamm-Wu theorem, and that gives me this particular formula. And so so now the question is that if I move away from 0, whether I can at least gain some log factors comparing to the starting point. And it turns out that yes, we can. So Balog, Treglam, and Wagner prove that actually instead you can drop these log factors when your alpha is between 0 and 1 minus 1 over r. And that will be the appropriate, the threshold function in this perturbed model, okay? And why is this upper bound 1 minus 1 over r? Again, Heinal-Semradi theorem tells you that under this condition, you already have perfect factors, so you don't need any help from the random edges. Okay, so they not only proved this result. Okay, so this result tells you that the upper bound on the threshold is equal to this. They extended this result not only for the perfect KR factor, but also for perfect H factor for every graph H, okay, when this alpha is at least 0. And when H is equal to KR, then this result that they prove is optimal for alpha at most 1 over r, okay? So they prove that for alpha ranging from 0 to 1 minus 1 over r, the threshold is bounded by n to the negative 2r. And when your alpha is close to 0, meaning it's bounded by 1 over r, then actually here you have equality, not this inequality. Okay. How would you find that such a result is such a result is optimal? Well, usually you consider some suitable multipartite graph. So for example, if your r is equal to 3 and you consider alpha between 0 and 1 over 3, then again, the graph that you will look at is the complete bipartite graph with partite sets of size alpha n and 1 minus alpha times n. So it will be kind of unbalanced one. Okay. All right. And so what will happen here, if you try to cover this graph by K3 by copies of triangles, if you use some vertices of A, you can cover at most 3 times size of the A of vertices. Okay. But that it's not enough to cover B. So here will be some large set that it's not covered. Okay. And that means you will need some linear number of triangle from G and P. Okay. And in order to have a linear number of triangles in G and P, okay, you need this particular threshold, n to the minus 2/3. Okay. Does it make sense? I hope so, right? So I start with this unbalanced bipartite graph. I throw at it a random graph, and I try to cover it by vertex disjoint copies of triangles. So if you take any triangles using the random edges of this form, okay, then of course the number of vertices that you cover in A and B is 3 times size of A at most. Okay, and the way how this is constructed, this is 3 times alpha n, and this is surely smaller than n, which is total number of vertices. So this remainder of edges, vertices must be covered by triangles from the random edges inside B. Okay, and so you have a linearly many vertices left to be covered, and for that you just need to do a little bit of random graph theory, and that tells you that such a threshold actually must be n to the minus 2/3. All right, so okay, so in some range we have optimality, but well, what happens if alpha is at least 1/r? All right, so what can be said then? Well, then Jihan, Patrick Morris, and Andrew Treglown came shortly after, and actually what they did, well, they proved the following result. So you look at K ranging between 2 and R, and you classify alpha based on to which of the interval based on K they belong. So for given K and R, if your alpha is between 1 minus K/R and 1 minus K minus 1/R, then they show that if you take P at least C to the n minus 2K instead of C to the n minus 2/R, then this perturbed graph contains a perfect KR factor. And they prove that actually this threshold is sharp. Okay, so lots of parameters and lots of words. So let me just look at the case when R is equal to 3, and that's summarized in this table. So if this is the case, then your K can be either 2 or 3. Okay, and then situation is as follows. Okay, if your alpha is equal to 0, then the threshold is given by this n to the negative 2/3 log n to the 1/3. That's a Johansson-Kanvu. If your alpha is at least 2/3, that's a Heinal-Semeredi. You don't need any random edges. All right. If your alpha is between 0 and 1/3, then by Yoshi Balog and co-authors, the threshold is n to the minus 2/3. Okay. And when alpha is between 1/3 and 2/3, okay, and that's the case when K is equal to 2, then the result of Han, Morris, and Treglown tells you that actually the threshold is not n to the 2/3, but the threshold is n to the negative 1. Okay, so you only need to throw in linearly many edges, okay, to be able to find a perfect K3 factor. So this is almost a perfect picture of the situation, except they don't cover the boundary cases. What happens at this points? You have strict inequalities here, right? It's not at most, it's really strict inequalities. So what happens when alpha is 1 over r, 2 over r, up to r minus 2 over r? Okay. And so for this particular case, when r is equal to 3, the only leftover case is alpha is equal to 1 over 3. And actually that was for us our starting point to look at this question. Okay. So when you look at this table and you would like to determine this threshold for alpha to be equal 1 over 3, then the first thing what you observe is that small constant times log n over n is not enough. Okay. So what do you do here? Well, it will be boring because again you take the suitable chosen bipartite graph. So actually what you do is you take bipartite graph when one set has size n over 3, the other set has size 2n over 3, and you take all edges in between them. Okay. And now imagine that you throw at it G and P, where P is of this form. So what you can do, so you can do some calculation. And so this set over here was independent set in my original graph. So if I throw in the random edges, the only edges that these vertices see inside are the random edges. Okay. So if you throw in G and P is at most log n over 2n, then you can estimate the number of C4s in number of triangles over here. Okay. So over here, you can calculate the number of triangles is actually just something like log to the 4 times n asymptotically almost surely. Okay, this is just the, for those of you who know a little bit, this is just the Markov's inequality and calculating some expectations, nothing more than that. Okay, so we have at most log to the 4 times n triangles coming from G and P in this set B over here of size 2n over 3. Okay. On the other hand, you have polynomially many isolated vertices. Okay, so you have a quite non-trivial set of vertices in that set B, which don't see any random edge. Okay, but what does it mean when we want to cover this graph by the triangles? Well, that means that every such a vertex must be covered by 2 edges coming from my original graph, plus some random edge over here, right? But if you want to cover the full triangle, for every such a vertex, because you took 2 vertices on this side, you have to take one triangle which is completely inside this set B, right? Just because you have this balance n over 3 to n over 3, right? So if you ideally you would like to do triangles like this, one vertex for here, edge here, and like that, right? But this tells you that for some of these vertices which are isolated in GMP, you cannot do it. So you unbalance it the other way around. And so to bring your balance back, you need a triangle completely inside. But again, you have many vertices in this small set over here, but you have at most this many triangles completely lying inside. So there is no way you can find a perfect K3 factor in this perturbed graph. Okay, and that tells you that, okay, you need to, okay, at least you have a lower bound on the threshold, right? Log n over 2n is not enough. We just found one example of such a graph. Okay, and then what we prove actually is that, on the other hand, if you take a suitable large constant c and you take p larger than c times log n over n, then this G 1/3 union G and P actually contains triangle factor. Okay, so that means that log n over n is what should go instead of this question mark over here. All right. So, okay, I put here two other statements, and they look kind of complicated, but let me just try to tell you meaning of these two theorems. So this first theorem tells you that if you take a graph G, which has minimum degree even a little bit below 1/3 times n, okay, but which is not close in added distance to extremal graph. So in other words, okay, it's not close to the graph that I described over here. It's complete bipartite graph with size n3 and 2n/3. So if your graph is with this property that it's not too close to this one extremal graph, then actually what you need is only linearly number of random edges. In other words, you just need your p to be constant over n. Okay, so this log n over n, is really just to work with this nasty piece of graph. Okay. All right, and then we prove also something which looks very, very nice. So we prove that if we are still allowed to take log n over n edges, then even for the graphs that goes below with min degree below n/3, you will be able to find, well, maybe not full triangle factor, but at least a minimum degree of the graph disjoint triangles in this graph. Okay, so for essentially for every vertex, I mean, for a delta G minimum degree of the graph vertices, you find disjoint triangles over here. Okay, and that's kind of very nice, right? I mean, it's so there is natural boundary, this n/3. So if your min degree is at least n/3, then you know that you have a perfect factor. If your degree is below n/3, you know that you cannot find a perfect factor, but you can find at least the min degree many disjoint triangles in your perturbed graph. Okay, so we kind of describe what's really happening around this cutoff of n/3 in terms of probability. And then you can actually make it a little bit more. You can say a little bit more. You can drop this log thing over here. Again, provided that this graph that you start with is again not this unbalanced bipartite graph. Okay, so it's really, one would say bipartite graphs are bad for you. You need more randomness to deal with them. All right. Oh, with time, I'm okay with time. So here is a glimpse into the proof. Okay. So, all right. I come from the school of Rodel, so I use regularity method whenever I can. But on the serious note, so we apply regularity method. So that means this is the method that allows you to take any graph which is sufficiently large and split it into disjoint bipartite random-like subgraphs. Then what we do, we use something called stability of vertex covers. So this I will possibly explain it on the next slide if we decide to go that way. Then we use something which is very popular lately, which is called the absorption method. And then we kind of use some very tailored embedding statement that allows us to combine certain type of graphs with random edges to find a nice triangle factors. So here is an example. Here is a lemma which tells you that for some choice of the parameters, if you have a 3 set V, U, and W, such that, okay, V has size n, U and W are slightly smaller than V. Okay. Between V and U and V and W, you have something that comes from regularity method. So between them, you have a bipartite graph, which is random-like. So it has density D, and the edges are uniformly distributed. Okay. So it looks like a random graph. And what you do between U and W, you have there a random bipartite graph where each edge is thrown in with probability P, and this probability P is at least this constant capital C over N. So under this assumption, you can prove that, you throw it between U and W, and also you throw these random edges into V. Okay. And so this embedding lemma tells you that you can find in this graph a triangle factor that covers all vertices of U, V, and W. Okay. And this is okay. So this is nice. Okay. So you need these edges, random edges in the set V, because V is slightly bigger than U and W. You might wonder, this is a very strange setup. If you know regularity lemma, then you would expect that U, W, and V are of the same size. If they were of the same size, then this constant over N wouldn't work. You will need constant times log N over N. Okay. But this is that nice trick that if you allow that one of the set will be larger than the other two, then actually constant over N actually will do. And this is kind of really statement that you will do in your actual embedding in the proving of our result. Okay. Now I would like to see all of you, how many of you are really frightened with whatever I just said. So this was a glimpse of the proof, and I hope you glimpsed long enough so I can either talk a little bit more, but I think I have about 10 to 15 minutes left, so I don't know whether I should really try to give you some glimpse, but maybe I will try. Okay. All right. So let me try to give you the proof. So I take graph G, which is this graph which has a mean degree at least n over 3. Okay. And I will assume it's non-extremal. Okay. Okay. So meaning that in any distance, it's not close to this unbalanced kn over 3, 2n over 3 graph. Okay. So, of course, the first thing that we do, we will use the regularity method. Okay. So what does it mean? Well, the graph gets split into vertex sets of the same size, such that most of the pairs are epsilon regular. Okay. So they are random-like. So what do we do? So here comes that part about the stability of vertex covers by k1/2 and k11. So what this means is that from this graph, you look into reduced graph, and you use the stability of the vertex cover, and what it will tell you is that you can split our original graph into cherries like this, that the graph, these bipartite graphs are epsilon d super regular. So that means these are random graphs, have density at least d, and every vertex involved has a large minimum degree. Okay. So the whole graph can be split into structure like this, and balanced bipartite super regular graphs. Okay. And then there will be some small class of leftover vertices. So for these vertices, you use the fact they have a large minimum degree, and you use some random edges to cover all of these by some vertex disjoint triangles. So this will be the absorption method. And you do this absorption method in such a way that this set and this set will be again much smaller or suitable smaller than this set. So that means that this embedding lemma on them will apply. Okay. And also what you will do that if you consider graphs of this form, this bipartite graph, then you remove just suitable many vertices from one side so that there will be slightly imbalanced. And then you use the random edges here and here to cover everything by the triangle. And on every cherry like this, you use your embedding statement, and altogether this will give you covering of your perturbed graph by the triangle. Okay. And of course, devil is in the details, and there are about 15 pages of the details. I think for the glimpse, this is probably good enough. All right. Now, what will happen if I want to consider factors with the larger cliques? Okay, so now we have a perfect picture for the triangle factor, right? For alpha ranging from 0 all the way to 1, we know exactly what the threshold should be like. Okay, so this was really what we did so far. Okay, so when you want to do, let's say, K4 factor, okay, then the first case that is not covered by this Treglan, Hahn, and Morris result is alpha is equal to 1/4. Okay, and when you look at some particular example, it will become clear that you will need, that a good, or you would conjecture that proper threshold is n to the negative 2/3 times log n raised to 1/3. The fact that this is the same as this number is not accident, because it just means that you need to find a large collection of triangles in the random graph somewhere in this example. Okay, and so you would hope that this would be correct threshold. It's in the same way like this turned out to be correct threshold because you needed some spanning structure that has threshold log n over n. Okay, so it's if you read this and understand how this really works, then you are not surprised by this number. Okay? However, shockingly, it turns out that this is not the right thing, which is bad and good, right? It's good in a sense that after this you might feel, okay, it will be easy, case closed. So this is still an exciting left open case. The bad news is that we still don't know what's happening, so it's kind of left open. Okay. So I will maybe show you why this is a false thing. But what again turns out is that if you are not in any distance close to some extremal case, then actually n to the negative 2/3 from here is the right threshold, right? So again, it's this multipartite graph which forces you to have something there extra than this n-2/3. Okay, and the similar behavior happens for non-extremal cases at every value of r that it's left open in these jumps, right? So there is something left to be done. Okay, so why this doesn't work? So what will be the graph that doesn't work? Well, the construction is kind of neat. So let me just show you. So what you do is you take two sets. One is set A, and that will have a size n/4 minus m. Then of course you will have a set B of size 3n/4 plus m. You take all the edges between A and B, So again, complete bipartite graph. Okay. And what you do inside here, you cover it by copies of complete balanced bipartite graph KMM. Okay. I put there C4 or K22, but it's imagine that it's KMM, and it's covering this set B. Okay. Does it make sense? Right. So you divide B to the sets of size to M, and on each such a set of size to M, you put a copy of KMM, complete bipartite graph. So this will be my G. Okay. So from this construction, it's clear that this graph has mean degree n/4, right? So if you look at any vertex on this side, it has all this set B as a neighbor. So it has degree 3n/4 plus m. And if you look at any vertex over here, it has n/4 minus m vertices as a neighbor in set A, plus m vertices in KMM as a neighbor. So it has degree n/4. Okay. So this is our graph G. Okay. And then I throw at it random graphs G and P, where my P is given by this formula. And I try to find a covering of this perturbed graph by copies of K4. Right? Okay. And now, how do I find? So how do I find these K4s? Well, so some of these K4s will use these vertices from A, right? So you will find K4 like this, maybe. Okay. But if you use copies that use at least one vertex from A, then you cover 4 times size of A vertices of the whole graph. 4 times n/4 minus m is n minus 4m. And that leaves you at least 4m uncovered vertices in the set B. Okay. And so that means you need to find at least another m copies of K4, which are only contained in the set B. Okay. Very good. And then you just do some first moment calculation. And you can show that even with this help of these KMMs that you have covering the whole set B, if you throw in these random edges, then you will not find there m copies of K4. Okay, it's a really some lengthy first moment calculation, and it just comes out. Okay, and so that means you cannot have a K4 factor covering whole graph. Okay. But what turns out even worse is, okay, so okay, I work with this probability, but it turns out that you can choose small epsilon, like 1/100. Okay, you actually take p to be n to the minus 2/3 with some epsilon. Okay, and you take some suitably chosen m to cover this b by km and m, and the same argument works again. Okay, so not only this doesn't work, it will not be n to the minus 2/3 here. It will be some n to minus something between n to the negative 1/2 and n to the negative 2/3, and it's not clear what it is. Okay, so it's not about guessing logs. It's actually about looking what will be the right power, and I somewhat don't have a good guess to entertain. Anyway. All right, so of course I promise I will tell you something about the universality, but given that I have 2 minutes to go, I probably need much more than just 2 minutes. Let me just go to at least one open problem. Okay, so open problem here is, of course, what happened for general H. Okay. So take your favorite H, and okay, Balog, Tregnam, and Wagner gave optimal threshold for perfect H factor if your alpha is smaller than 1 over size of h, okay? But unless your h is cycles that we did in the separate work or clique, it's not clear how this all should work, okay? So if you don't like particularly this clique and just looking at these boundary cases, 1 over r, 2 over r, etc., well, if you can look at some particular class of graph H and try to see what do you get if you look more carefully at this Pollock, Treglan, Wagner, etc. All right, and then there is another question about the universality, but maybe because we didn't touch really universality, then thank you very much. And if you have any questions, I'm ready for your questions.
All right, thank you. Questions?
So do the random edges make the absorption lemmas easier?
They help, right? That's so we always use them in degree, and then of course one of the property you use is that because you have a linear size, the min degree, and if you look into it, then on every linear size of the set you will find an edge in it, right? So that will allow you to build triangles, etc. So that's the basic how you marry these two together. Right? So, I mean, the good thing is we not always look for things just in the random graph. For that, you need usually this extra factor of log. But if you are somewhat unbalanced and you have this large min degree, then the linearly many random edges, you can already do something with them. Right?
So is there anything where if you look at, sometimes you consider small alphas or like alpha equals 1/3 minus a little bit.
Mm-hmm.
If you let that little bit tend to 0, then can you say something about the log factor? Like, for example, just in the alpha equals 0 case, if instead you have a sublinear minimum degree graph.
We didn't look at what happens when you do this fine transition, right? I mean, probably something interesting happens there, right? Because but we don't know. So, I mean, if you really want an interesting case to play it, I think it's this one, the one that I showed you, right?
Yeah.
What happened? I mean, if anybody would like to try, then maybe this is really the easiest example to dive in and try to see what sort of transition is happening over here at 1/4, right? It's because clearly you will transition from here to here somewhere.
Do you have a bound on that? So you know what doesn't, you don't know what does work. Do you know what doesn't work? Or is the open problem simply -1/2 to -2/3? And you don't know anything beyond that?
I think after these examples, we kind of decided we wanted to go for the universality and the square of Hamilton cycle. So we kind of left this. It became too niche and it wasn't clear what it should be. And it felt like just playing with some example, and we were not too excited about this maybe, and maybe we were much more excited about the other results. Right?
So on the topic of universality, you were saying that the n equals 3 case is much harder than the n equal, or the
Yes.
maximum degree 3 case is harder than the maximum degree
Yes,
2 case.
and the reason is that for 2 universality, when you try to find a graph, a threshold for the property that you find any graph with maximal degree at most 2, it essentially reduces to finding a square of Hamilton cycle because it contains all of these graphs. So we were kind of happy that we were able to find a threshold for appearance of the square of Hamilton cycle in this perturbed model, because it nicely fit with the Barghaus and recent works, right, on the threshold for the square of Hamiltonian cycle in GNP. So we kind of were able to determine this this threshold for the square, and because the square of Hamilton cycle contains any graph with maximum degree of 2, then this allowed us to find this, determine this threshold for 2 universality. Okay.
Would it maybe be possible to sort of continuously move between like the 2 maximum degree 2 and 3 case by considering like universality, where I'm looking to contain all graphs whose average like maybe looking at the average degree instead of the maximum degree?
I think maybe the main thing here is that as soon as you have expanders in your family, expanders are difficult to embed, right? That's so. I think that was our main problem, right? That if you didn't have any expanders, then I would sort of say maybe we know what to do, but since I have a graph that they expand, we didn't try too hard to see what it should be, right?
Oh, I guess maybe this is what I mean instead, right?
Yeah,
Because
yeah.
maybe I want consider a family bigger than the ones with maximum degree 2,
Yes.
for which the average maximum degree is, so look at all the graphs in your family, the average maximum degree is bigger than 2 but smaller than 3. Is it possible to say anything if I consider?
Honestly, we didn't look at this carefully. We were interested to see whether we can do anything for 3 universalities, but since we wanted to sort of say something about the full family, we run into problems of, as I said, with these expanders, and then kind of give up relatively quickly because we had no good idea how to proceed.
Okay, thanks for your talk.
Sure.
Any other questions? All right, then let's thank Jozef again.
Thank you.
Thank you, Joseph. This was very nice. And I guess we will meet again next Friday.